master slave GK flip-flop. Registers. Registers are used to store multiple bits. A flip-flop can store logic 1 or logic 0. So it is a basic memory element which can store one bit of information. But a register is also a memory element which can store more than one bits. So if you want to store 4 bits, we will use 4 flip-flops to design a register, and these 4 flip-flops will hold 4 bits, 4 bit information. So it will be a memory element to store multiple bits. Also there is one purpose where registers are used. This one is that registers are used to convert serial data into parallel data, or parallel to serial, or parallel data to serial data. So for serial to parallel or parallel to serial conversion, registers may be used. There are 4 types of registers that we will study. One is serial input, serial output, that is SISO. Next one is serial input, parallel output, that is SIPO. Parallel input, serial output, that is PISO. And last one is parallel input, parallel output, PIPO. Now in all these registers we will use shift registers. Shift register, we'll see what is a shift register. Suppose this is a register in which we have these 4 blocks where 4 bits can be stored, and here we have applied a clock. Suppose there is input 1001, and here we will apply 1111 input. Now when clock is applied to the flip-flops in the shift register, then after each clock pulse, one bit will enter here and other bits will be shifted further. After every clock pulse, one bit will be shifted, or every bit in the shift register will be shifted one position right. So every clock pulse, with every clock pulse, data is shifting to the right hand side. So this register can be called as right shift register. These shift registers we will use for our purpose. Right shift register. Now first we will start with serial input, serial output shift register. Serial input, serial output shift register. In serial input, serial output shift register, we will have some flip-flop. We will design it for 4 bits. We will use here age triggered flip-flop. Remember this thing that if flip-flop is shown with this sign at the clock, it will be positive edge triggered flip-flop. And if flip-flop is shown with this sign, it will be negative edge triggered flip-flop. And if flip-flop is shown with this sign, it will be positive level triggered flip-flop. And if flip-flop is shown with this clock, it will be a negative level triggered flip-flop. Now in this shift register we have all the flip-flops with positive edge triggering. Here we will use D flip-flops. This will be D3 bits, Q3, Q2, Q3 bar, D2, Q2, Q2 bar, D1, Q1, Q1 bar, D0, Q0, Q0 bar. Now in this serial input, serial output shift register, the serial input will be applied at this input of the first flip-flop and serial output will be taken at this flip-flop, and this will be the clock pulse to trigger the flip-flops. Now simultaneously we will see its waveform. Suppose we have applied a input 1001. Initially all the flip-flops are in reset mode, that is all the flip-flop have stored 0, logic 0. Remember the one thing that if a flip-flop has 0 stored in it, then this 0 will be available at its output. So all the flip-flop have logic 0 at its output. So in the waveform we will draw all the outputs. Now this is the clock. All the flip-flops are designed for positive edge triggering. So we will look for positive edge of the clock. Now initially all the outputs are at logic 0. Now we will see the change in the output of each flip-flop after first clock pulse. First positive edge means first clock pulse. Second positive edge means second clock pulse. Third, fourth, fifth. Now we'll start. 1001 is the input serially will be applied to the first flip-flop. Now before applying the clock pulse, we must arrange the input of all the flip-flop. Remember here all the flip-flop will be triggered at the same time. So don't do this mistake. If this output changes from 0 to 1, this 1 will be input for this flip-flop. This is not true because both the flip-flop will be triggered at the same time. So if input the previous output for this flip-flop was 0. This previous output itself will be input for this flip-flop. Now we'll start the operation. Initially all the flip-flop have logic 0 stored in them. For this flip-flop, this first bit 1 will be input. This 0 will be input for this flip-flop. This 0 will be input for this flip-flop, and this 0 will be input for this flip-flop. Now start the operation. At the first positive edge, all the flip-flop will be triggered, and we know that all the flip-flops are D flip-flop. In D flip-flop, the next output is equal to the D input. So for this flip-flop, the input is logic 1, output will become logic 1. Q3 will become logic 1. Now remember one thing, that this flip-flop now stores logic 1. This will be available at output. This will go input here. Is not a true, because this output logic 1 will be available for this flip-flop in the next clock pulse. But for this clock pulse, input is logic 0, this 0. If input is 0, output will be 0. Q2 will be 0. For this flip-flop, input is 0, output will again be 0. For this flip-flop, input is 0, output will be 0. So after first clock pulse, only Q3 changes from 0 to 1, and all other inputs, all other output are at the same level, that is logic 0. Now the second clock pulse will be applied. For this second clock pulse, we will arrange all the input first. Now we know that for the first flip-flop, D3 flip-flop, its output Q3 is logic 1, means this flip-flop stores logic 1, other 3 flip-flops store logic 0. Now for this flip-flop, it stores logic 1, its output will be logic 1. It stores logic 0, output will be logic 0. It stores logic 0, output will be logic 0, and this logic 0 will be available here output, which is of no use. Now this second bit will come as input for the first flip-flop. Now we'll start with the second clock pulse. If second clock pulse is applied, this 0 will store in this flip-flop, means Q3 will change from 1 to 0. For this flip-flop, input is logic 1. So when flip-flop triggers, this 1 will be input and it will be stored in this flip-flop. So Q2 will go high because logic 1 is now stored in this flip-flop. So for this flip-flop, input is logic 0, output will be again logic 0. For this flip-flop, input is logic 0, output will be logic 0 again. Now this flip-flop has logic 0 in it, this flip-flop has logic 1 in it, this flip-flop has logic 0 in it, and this flip-flop has logic 0. Now for the next clock pulse, we will first arrange all the inputs. At this flip-flop input, the third bit will be ready, logic 0. For this flip-flop, input will be this logic 0. For this flip-flop, input will be this logic 1. For this flip-flop, input will be this logic 0. So when third clock pulse applied, this 0 will be stored here. So Q3 will be 0 again at the third clock pulse. For this flip-flop, input is logic 0, so output will again logic 0. For this flip-flop, input is logic 1, so if this one will be stored in this D flip-flop and its output will be logic 1, so Q1 will become logic 1 at the third clock pulse, and at the last flip-flop has logic 0 input, so its output will be logic 0. Now for the fourth clock pulse we will arrange all the inputs. Now this fourth bit will be input for this first flip-flop, while uh, Q3 is logic 0, so this flip-flop stores logic 0. This will be available as input to this flip-flop. Q2 is logic 0, so this flip-flop stores logic 0. This will be available as input for this flip-flop. Q1 stores logic 1, so this logic 1 will be available as input for this flip-flop. Now when we apply fourth clock pulse, at this fourth clock pulse, this logic 1 will be stored here. So Q3 will be logic 1. This logic 0 will be stored here. So it will be again logic 0. This logic 0 will be stored here. Earlier the output was logic 1. Now the output will be logic 0. And this 1 will be stored here in this flip-flop. So at the fourth clock pulse, Q3 is 1, Q2 is 0, Q1 is 0 and Q0 is 1. 1 0 0 1. This data is now stored in this flip-flop. Now this data is stored in the flip-flop. Remember one thing, that initially all the flip-flop had 0 0 in them. Now after first, second, third, fourth clock pulse, all the bits are inputted to the register. So for loading n bits or for loading 4 bits, we required 4 clock pulse. So for loading n bits, we will require n clock pulse. So for loading the serial data in a shift register, we will require if we have 4 bits, 4 clock pulses are required. If we have n bits, n clock pulses are required for loading the serial data in a shift register. Now if we want to take all the bits out, we'll again apply the clock pulse, and this data 1, then 0, then 0, then 1 will be taken out serially at its output. Remember one thing, when all the bits are stored in these flip-flops, all the input serial data are stored in this flip-flop, that is 1 0 0 1 is stored in this flip-flop. Now this logic 1 is readily available at the output, means we need not apply a clock pulse to take output of this flip-flop, and to obtain the other 3 bits from this flip-flop at the output serially, we need to apply 3 clock pulse to shift the data to the right hand side by 3 position. If this one is shifted right by 3 position, 1 2 3, it will be taken at the output. So 1001, this data will be taken at the output. 4-bit data can be taken at output by applying only 3 clock pulse, because 1 bit output Q0 is readily available at the output. We need not apply any clock pulse. We want if we want other 3 bits at the output, we need to apply 3 clock pulse. So 3 clock pulse will be sufficient to obtain 4-bit data at the output. Now if you want to obtain n-bit data serially out at the output serially, if you want this n-bit data, we need to apply n-1 clock pulse. So after n-1 clock pulse, the serial output will be obtained. Now we'll see the next shift register, that is serial input, parallel output. This is the important shift register which is asked in the examination. In serial input parallel output shift register, the design will be similar to the earlier one. And now we will design only 3 bit. So 3 flip flops will be used. Again, there will be D flip flops. Now this was the earlier serial input serial output register. The only difference is the output will be taken simultaneously. This output will be Q2, Q1, Q0. So this time the output will be taken parallelly, and this is serial input. Now remember one thing, there are 3 flip-flops, 3 bits can be stored. Earlier we have seen there were 4 flip-flop. For 4 bit storage we need to apply 4 clock pulse. For 3 bit storage we need to apply 3 clock pulse. So for n bit input, n clock pulse will be required. Similarly, if you want to take the data out, earlier for 4 bits, 3 clock pulses were required because the last flip-flop output was readily available at the output. We need not apply any input, any clock pulse. Now, suppose we have these flip-flop with bits 101. So, if you want to take these bits at the output, remember one thing, that this one stored in this flip-flop is available at the output. This 0 stored in the flip-flop is available at the output. This 1 stored in the flip-flop is available at the output. And these available bits can be taken directly here at the output. So for output, 0 clock pulse is required. We will summarize all these things at the end. So for serial input, serial output shift register, for input 4 bit, 4 clock pulses were required. For output 4 bits, 3 clock pulses were required. And in serial input parallel output shift register, for inputting 4 bits we required 4 clock pulses, but for taking the 4 bits at the output we need not apply any clock pulse. All the bits can be taken at the output directly if they are stored in the flip-flops. Now the next flip-flop is parallel input serial output. This register has a very complicated design. We'll draw 3-bit register. Now this will be input bit D2 and this will be input bit D1 and this will be input bit D0. This device will be a 2:1 multiplexer which will multiplex the input and the serial transfer of the data. The design will be like that, and the select line of these multiplexers will be taken out. This will be clock, this will be control input. Now the data can be applied parallelly, but for that the control input should have the desired value. If at the control input we have logic 0, then the upper input will be connected to the output. Upper input will be connected to the output, and these flip-flops will take an input from these bits D to D1, D0. Now if control input has logic 1 value, for this logic 1, this will be connected to the output, this will be connected to the output. In this case, the data will be shifted serially, means serial connections will be established. So serial output can be taken at the output of this flip-flop, while data can be inputted parallelly. But for that we have to apply a suitable value of the control input. Now we'll discuss on the clock pulses required for parallel input and serial output. For parallel input, we can input all the bits to the flip-flop, provided they must be triggered. So if all the bits are simultaneously available at the input of the flip-flop, if we apply a clock pulse, all the bits will be stored in the flip-flop. So for single clock pulse, any number of bits can be stored in the flip-flop. So for parallel input, we will require only one clock pulse to input the data. Only clock pulse to input the data. Now, for taking the data serially at the output, if the data is stored in the flip-flop, we know that earlier we had 4 bits. For taking the 4 bits at the output, we require only 3 clock pulses. So for n bit we will require n minus 1 clock pulses. So for serial output there will be a requirement of n minus 1 clock pulses at the output. Sorry. So for taking the data serially at the output, there will be requirement of n minus 1 clock pulses, and for inputting n bit data, we will require only one clock pulse. Now the last flip-flop is parallel input, parallel output shift register. Now this is the parallel input, parallel output shift register. In this parallel input, parallel output shift register, D2, D1, D0, all these are bits from where data can be inputted parallelly. For this, one clock pulse is required, and we know that for taking the data at the output parallelly, we don't require any clock pulse. So we will summarize all the clock pulses required for all these flip-flops. Serial input, parallel output, serial input, serial output, parallel input, serial output, parallel input, parallel output. For input and for output. We know that for inputting the data serially will require the clock pulses equal to the number of bits. For n number of bits, n clock pulses will be required. So total time will be n into t clock. For taking the data at the output, we will require n minus 1 clock pulses. For 1 clock pulse, the time is t clock. So for n minus 1 clock pulses, the time will be n minus 1 into t clock. For serial input data, in serial input parallel output shift register, will require n clock pulses again. For parallel output, we will not require any clock pulse. For parallel input, we will require 1 clock pulse, and for serial output, we will require n minus 1 clock pulse. For parallel input, we will require 1 clock pulse, and for parallel output, we don't require any clock pulse. So this was all about the shift register. One thing is that in shift registers, if data is shifted to the right, for example, we have uh, some data 1111 in this flip flop, and we have again one input here. If data is shifted, or these four ones are stored in the flip flop, and now we have input 000. If the data is shifted to the right, this one bit 0 will be added here, so the data will be 0111, and this one will be taken at the output. So the decimal value of this is 15, and the decimal value of this is 7. Data will be uh, reduced. Now we'll take one example on shift registers. A 4-bit serial input parallel output right shift register is initially loaded with 1011, what will be the data after 3 clock pulses. Now we are given this figure. Now we'll start the operation. Initially the data is 1011, and the clock pulse will be called as 0. When we apply the first clock pulse, we will change the output or data of this shift register, but for that first we have to arrange this bit. If it is 0 or 1, these two bits will be XORed. So 1 XOR 1 will be 0. This 0 will be XORed with this 0 will be 0. Means the next input bit will be 0. So a 0 bit will be inserted to the register, while the other bits will be shifted to the right. Now these two will be all XORed, answer will be 1. These two will be XORed, answer will be 0. Again 0 will be inserted, so 0 and other bits will be shifted. Now these two bits will be XORed, 1 will be answer. These two bits will be XORed, 1 will be answer, and this 1 will be inserted in the next clock pulse. So this 1 will be here and other bits will be shifted to the right. So the data after 3 clock pulse will be 1 1 0 1. So